Today, we're embarking on a very special deep dive. We're looking into one of the universe's most fundamental forces, gravity.
Right?
You've brought us this analytical report exploring an alternative, kind of intriguing idea, a matter density drag model of gravity.
That's right. Yeah, this concept suggests gravity isn't quite what we think. It suggests it's a drag effect.
A drag effect.
Yeah, from a sort of thickening of matter density near massive bodies. And this thickening, the idea goes, slows time because clocks are physically impeded somehow.
So it's trying to find a physical mechanism.
Exactly. A modern take on that age-old quest.
Yeah.
To find a physical reason for action at a distance. It's often set up against general relativity and curved spacetime.
Okay, so our mission today is to really unpack this matter density drag idea,
Dig into it.
put it in historical context, test it, rigorously against observations.
See how it holds up.
And then compare it with our established understanding, with general relativity.
Yeah.
Think of this as your shortcut to understanding not just what these ideas are.
But why one prevails.
Exactly. And what that really means for how we see the universe. Let's unpack this.
Sounds good.
Okay, so before we dive into the specifics of this model, the report suggests looking back, history, right?
Yeah, absolutely. History is crucial here.
Which?
It shows how intuitive ideas get put through the scientific ringer.
See what sticks.
Precisely. The idea of gravity as mechanical, like a push or a drag, it's not new at all.
Right.
So we're going to look at two big historical ones. Lesage's push gravity and the whole ether drag idea.
And this isn't just to knock them down?
No, not at all. It's about understanding the process, how science works, propose, test, refine, or sometimes
Reject.
reject. Exactly. Understanding why things didn't work is just as important.
Okay, let's start way back. 18th century. Georges-Louis Lesage, what was his proposal?
So Lesage, and he was building on some earlier ideas too, he pictured the universe filled with these things he called ultramundane corpuscles.
Ultramundane.
Yeah, basically it means beyond the world. Tiny, invisible particles flying incredibly fast in all directions, constant bombardment.
Okay, busy universe. And the mechanism for gravity. How did that work?
The core idea was shadowing.
Shadowing.
Yeah. An object alone in space gets hit equally from all sides. No net force, right?
Makes sense.
But put two objects near each other, like the Earth and Moon. They shield each other from some of those particles coming from the direction between them.
Ah, so less push from the inside.
Exactly. Creates an imbalance. More push from the outside than the inside, so they get pushed together.
Yeah.
An apparent attraction.
Clever.
He even figured matter must be mostly empty space for these particles to get through and push on all the bits inside to make the force proportional to mass.
Ingenious, but you said it faced fatal flaws.
Oh, big time. Quantitative objections it just couldn't overcome.
Fatal how? Tell us more.
Well, the biggest killer was the thermal crisis. See, for the particles to push, the collisions can't be perfectly bouncy, perfectly elastic. Some energy has to transfer.
Okay. Like friction, almost.
Sort of. And in the late 19th century, physicists like Maxwell and Poincaré, they did the math. They calculated the energy dumped into Earth by this constant bombardment, and it was immense, enough to heat the Earth to vaporization in a fraction of a second.
Vaporization? Whoa.
Right. Completely violates energy conservation and, clearly doesn't match the nice, cool Earth we live on.
Clearly. Okay, that's pretty fatal. What else?
Another major one, and this is really relevant for any drag model, is the orbital decay problem. A planet moving through this sea of particles, orbiting the sun, it's constantly running into a headwind.
Right.
Right? A drag force.
Like driving in the rain.
Exactly. And that drag saps energy. The planet should lose orbital energy and spiral into the sun.
But they don't.
They don't. Our solar system's been stable for billions of years.
Yeah.
That stability is maybe the simplest, strongest evidence against these kinds of models. Lesage even tried proposing super fast, faster than light particles to minimize drag.
Which causes other problems.
Oh, yeah. Made the heat problem worse. And doesn't work with modern physics anyway.
So the mechanism for attraction also destroys the system. A definite deal breaker.
Precisely. And one more quick one. The aberration problem. Laplace figured this out.
What's that?
If gravity travels at a finite speed, like these particles must, the force wouldn't point directly between two bodies.
Yeah.
It would point to where the other body was a moment ago.
Because of the travel time delay.
Right. That slight offset creates a sideways push, a tangential force, that destabilizes orbits. It would actually make things spiral out, not in, or at least mess things up badly.
Okay, so Lesage's idea, while clever, just didn't hold up quantitatively.
Not even close, unfortunately.
What about the other idea, the luminiferous ether? The medium for light? Did people try to use that to explain forces?
Absolutely. That was a huge concept in the 19th century. The big question became, is this ether stationary? Or does Earth kind of drag it along as it moves?
Right. I remember the Michelson-Morley experiment tried to detect our motion through a fixed ether.
And famously found nothing, which led some people to think, okay, maybe the Earth drags the ether along with it completely.
Right.
That would explain the null result.
Makes sense. But was there a test for that idea? Complete ether drag?
There was, and it came from a really simple, elegant astronomical observation. Stellar aberration.
Stellar aberration. Okay.
James Bradley discovered it way back in 1728. It's this tiny yearly shift in the apparent positions of stars as Earth goes around the sun.
This is the umbrella in the rain analogy. You tilt the umbrella forward when you walk.
That's the perfect analogy,
Yeah.
yes. You tilt it because of your motion relative to the falling raindrops.
Okay.
So the key implication is, if the ether was totally dragged along with Earth, like the air inside a moving car.
Then relative to the telescope moving with Earth, the light from the star would just come straight down.
Exactly. No tilting needed. No stellar aberration.
But we do observe it.
We do. And the amount we observe, about 20.5 arcseconds, perfectly matches the ratio of Earth's speed to the speed of light.
Yeah.
It's conclusive proof the ether isn't being fully dragged.
Wow. So one precise measurement takes down a whole concept.
That's the power of quantitative testing in science. A beautiful, intuitive idea can fall to a single, hard number.
Okay, so we've seen historical mechanical models hit these major roadblocks, energy problems, orbital decay, conflicts with observation. Let's bring it back to the present, this matter density drag model. How does it fare under the same scrutiny?
Well, our analysis in the report shows that fundamentally it shares that same mechanical philosophy. And because of that, it unfortunately inherits many of the same really insurmountable problems. Plus, it runs into new issues with modern evidence.
Okay, let's compare directly. The model says gravity comes from a medium of the smallest pieces of matter yet to be discovered. Any candidates in modern physics?
Well, the obvious candidate for undiscovered matter is dark matter, right? We think it's about 85% of the universe's mass.
Right. But what properties would this drag medium need?
To cause drag, it would have to be, interactive,
Hmm.
viscous, maybe. It needs to impede motion.
Oh, okay. And what do we know about dark matter's actual properties?
We know from a ton of evidence pretty much the exact opposite. Think about colliding galaxy clusters, like the famous bullet cluster.
Yeah, I've seen images of that.
In those collisions, the regular matter, the gas clouds, smashes together, slows down, heats up. Big interaction.
Okay.
But the dark matter halos from the two clusters, they seem to just pass right through each other. Almost no interaction at all.
So dark matter is collisionless, ghostly.
Pretty much. It interacts via gravity, sure, but not really with itself or with normal matter in any other significant way. That's why it doesn't easily clump into stars or planets, no friction to slow it down.
So that's a huge contradiction. The drag model needs interactive stuff.
And the most abundant unknown stuff, dark matter, is observed not to be interactive in that way. So this proposed medium would have to be something else entirely, something we have zero evidence for.
Okay, problem number one. What about the mechanism itself? Drag causing acceleration towards a body, and Galileo's finding.
Right, another big hurdle. First, like we said, drag usually opposes motion and depends on velocity, area, not mass. Gravity pulls things based on their mass, regardless of size or shape, as Galileo showed.
Feather and bowling ball.
Feather and bowling ball, exactly. Hard to see how a thickening medium explains that fundamental property.
And the direction.
Yeah, drag opposes motion. For something falling towards Earth, gravity accelerates it in the direction of motion. So is it drag or is it pressure? If it's pressure, like a denser medium pushing more,
Then you're back to Lesage.
you're basically back to Lesage, yeah.
Yeah.
And you inherit the thermal crisis and the orbital decay problem all over again. Our stable solar system, after 4.5 billion years, is just screaming evidence against simple drag.
Okay, so major issues with the medium and the mechanism. What about time dilation? The model says clocks just tick slower in the denser medium near mass. Simple, intuitive.
It sounds simple, yeah. But this is where it hits a really hard quantitative wall. We can test this very precisely using GPS.
The global positioning system relies on super accurate clocks in orbit, right?
Atomic clocks, yes. And their accuracy hinges on correctly accounting for relativistic time effects. Here's the crucial part. There are two different opposing effects for GPS satellites.
There's two effects.
Yep. First, kinematic time dilation. That's from special relativity. Because if satellites are moving really fast, like 14,000 kilometers an hour.
Their clocks run slower than clocks on the ground.
Right. By about 7 microseconds every day.
Okay, one effect. Speed slows time. What's the second?
Second is gravitational time dilation. That's from General Relativity. Because the satellites are way up high, about 20,000 kilometers, in a weaker gravitational field.
Their clocks run faster than ours on the surface.
Correct. By about 45 microseconds per day. Much bigger effect.
So slower due to speed, faster due to altitude. What's the actual measured net effect?
The net effect, what engineers have to correct for constantly, is that the satellite clocks gain about 38 microseconds per day compared to ground clocks. Faster overall.
Okay, 38 microseconds faster. How does this break the matter density drag model?
Because that model offers only one reason for time change. The density of the medium. It might explain the gravitational part, less dense, higher up, clocks faster. Maybe. But it cannot possibly explain the slowing due to velocity at the same time. How could the medium be less dense at altitude, making clocks faster, but also somehow more impeding just because the satellite is moving fast through it?
It would need contradictory properties.
Exactly. The medium's thickness or drag would have to decrease with altitude and increase with speed. Makes no sense. General relativity, though.
It handles both.
It handles both, naturally, from one consistent framework, the geometry of spacetime. GPS isn't just evidence for relativity. It's a daily, practical falsification of these simpler single-cause mechanical models. The old Huffail-Keating experiment with clocks on planes showed the same dual effect.
Wow. Okay, so the intuitive explanation completely falls apart against real-world data.
Quantitatively, yes.
All right. We've really put the drag model through its paces alongside its ancestors and found some serious shortcomings.
To put it mildly.
So now let's turn to the champion. General relativity, often dismissed as just imaginary curved spacetime. What does the report clarify here? Why does it prevail?
Well, that dismissal, imaginary, it usually comes from misunderstanding what curved spacetime actually means. GR isn't just pulled out of thin air.
It's built on something.
It's the logical result of combining a deep physical principle with known facts. Its power isn't necessarily intuitive appeal. It's often counterintuitive. Its power is in its predictions. Verified predictions.
And it starts with Einstein's happiest thought.
That's the foundation, a principle of equivalence.
Remind us what that was.
He imagined being in a sealed box, an elevator maybe. You can't tell if you're sitting still on Earth feeling gravity, or if you're in deep space accelerating upwards at 9.8 meters hours.
The feeling, the effects inside the box are identical.
Identical. You feel pressed to the floor, things fall the same way. No experiment inside can tell the difference.
So gravity isn't really a force in the usual sense.
That's the profound implication. If gravity is perfectly mimicked by acceleration, maybe gravity is just a feature of your reference frame. Objects in free fall, astronauts orbiting, a drop ball, and vacuum, they aren't feeling a force. They're following the most natural path possible.
Straight lines, essentially.
Inertial paths, geodesics. What we feel is the force of gravity is actually the floor pushing up on us, preventing us from following that natural free-fall path.
Okay, if gravity is like acceleration and acceleration affects everything, it must affect light too.
Exactly. Picture that accelerating elevator again. Shine a flashlight beam across it. By the time the light hits the far wall, the elevator has accelerated up slightly.
So inside the elevator, the light beam looks like it curved downwards.
Right. So by the equivalence principle, gravity must do the same. Gravity bends light.
And if light's path, which we think of as straight, can be bent,
then the underlying geometry of space itself isn't the flat Euclidean geometry we learned in school. Curvature is just the mathematical way to describe a geometry where the shortest path between 2 points of geodesic isn't a straight line in the flat space sense.
The bowling ball on the rubber sheet analogy comes up here a lot. How helpful is that, really?
It's okay for a basic visual, showing mass distorting something. But it's easy to misinterpret. Spacetime isn't a 2D sheet.
Right.
GR is really a theory about measurement. It says mass and energy change the rules for measuring distance and time. The Earth orbits the Sun not because of a pull, but because it's following the straightest possible path through the 4D spacetime curved by the Sun's mass.
Okay, it's a geometric theory. But how do we know it's right? What's the proof?
Proof in science comes from testing predictions. Precise, quantitative, falsifiable predictions. GR has made many, and they've been confirmed again and again.
Give us the highlights. the big ones.
Well, the precession of Mercury's perihelion was huge. Its orbit wasn't quite behaving according to Newton's laws. There was this tiny extra wobble, 43 arcseconds per century.
A known problem.
A known problem nobody could solve. Einstein applied GR, the equations for space-time curvature near the sun, and bam, it predicted exactly 43 arcseconds. No fiddling.
Wow. That's compelling. What about bending light?
Eddington's 1919 eclipse expedition was the first big confirmation. Measured starlight bending around the sun, just as GR predicted. Now, gravitational lensing is a standard tool in astronomy. We see massive galaxies bending light from things behind them, acting like cosmic telescopes. It's real.
So curved spacetime is observable, and what about that drag idea? Does GR have anything like that?
It does, but it's much weirder and more subtle than simple fluid drag. It's called frame dragging, or the lens-thirring effect.
Frame dragging?
Yeah, a rotating mass, like Earth, doesn't just curve spacetime, it twists it. It drags spacetime around with it.
Twists spacetime itself.
Wild, right. It's not a slowing down force. It's a twisting of inertia. And incredibly, this tiny effect was measured by the Gravity Probe B satellite.
How?
Ultra-precise gyroscopes in orbit. Over a year, their orientation shifted by the exact tiny amount GR predicted due to Earth twisting spacetime around it. Mind-blowing precision.
That is absolute mind-boggling. Okay, and the ultimate confirmation. Gravitational wave.
The smoking gun. Predicted by Einstein in 1916, directly detected by LIGO in 2015. Ripples in spacetime itself.
Not through a medium, but the medium itself rippling.
Exactly, caused by things like black holes merging. These waves travel at light speed, stretching and squeezing space as they pass. LIGO measured changes thousands of times smaller than a proton's width.
Unbelievable sensitivity.
And the waveform, the signal they detected, it perfectly matched the predictions from GR for merging black holes. Direct evidence that spacetime is dynamic, geometric.
Okay, this has been quite the journey. Comparing the intuitive drag model with the, well, established power of general relativity. So the final verdict on matter density drag.
When you hold it to the same standard, when you ask for quantitative predictions and check against evidence, it just fails on multiple fundamental levels.
Recap those for us.
Okay. Like Lesage, any drag or pressure model faces the energy and orbital decay problems predicting heat death and instability we don't see.
Check.
It needs an interactive medium, but the best candidate, dark matter, is observed to be collisionless, the opposite property.
Right.
Its simple explanation for time dilation is flat out falsified by GPS data, which shows two relativistic effects, not one.
The fatal flaw there.
And fundamentally, it offers no quantitative way to explain Mercury's wobble, the exact angle of light bending, frame dragging, or the existence and shapes of gravitational waves. It just doesn't predict these known phenomena.
So it really just boils down to predictive power.
Absolutely. That's the currency of science.
Yeah.
Not how intuitive something feels, but does it make precise, testable predictions that match reality?
And the drag model doesn't.
It's a qualitative idea, a speculation, that runs counter to evidence and fails to predict things we do observe. General relativity, counterintuitive as it might seem.
Works.
It works astonishingly well, from GPS in your phone to colliding black holes billions of light years away. The argument isn't about which feels right, but which accurately describes the universe.
An amazing tour through the fabric of reality itself. But is GR the end of the story? You mentioned problems, even it has.
Oh, absolutely not the final word, and that's important. Physicists know GR is incomplete.
How so?
It's fundamentally a classical theory. It doesn't include quantum mechanics.
Yeah.
And its own equations break down at extreme points, the singularity inside a black hole, the very beginning of the Big Bang. It predicts its own failure there.
So we need something more, a theory of quantum gravity.
We do. That's one of the biggest goals in physics. But, and this is crucial, any future theory has to obey the correspondence principle.
Meaning
Meaning it has to include all the successes of GR, where GR works well, solar system, GPS, gravitational waves. The new theory must reproduce those same results. It builds on GR, extends it, it doesn't just throw it away.
building on what works, not starting over.
Exactly. That's how science progresses.
So in conclusion, that curiosity, that drive to question and propose alternatives, like the matter density drag idea, that's vital for science.
It's the lifeblood.
Yeah.
Absolutely essential. But for an idea to move from speculation to theory, it needs more than plausibility. It has to survive that tough testing process. Quantitative prediction, experimental verification.
The gauntlet.
The gauntlet. And it's a gauntlet that mechanical drag models have consistently failed, while general relativity has succeeded for over a century. It remains our best description for now of gravity and the universe it shapes.
An incredible deep dive. Hopefully this gives you plenty to think about, maybe inspires some further exploration. What stands out most to you about that difference between an intuitive hunch and hard-won scientific evidence?
It's a fascinating contrast.
Thanks for diving deep with us. Until next time, keep that curiosity alive.